In this paper, we present fatigue crack paths in aluminum alloy panels with 4 stringers and 3 clips. In this slide, you can see the list of authors. Motivation for this research, as it was performed experimentally first, was a challenge that A380 Airbus faced after Qantas Flight 32 engine failure incident, because cracks were discovered in wing fittings. Therefore, many aircrafts were immediately tested, and in some cases cracks were also detected, and those fittings were replaced. Then all of A380 aircrafts were tested, and finding was that the problem is minor. It was not expected that it would affect operations, and that was right. But in any case, extensive experimental research was performed. Here we can see stringer panels with 4 stringers with an aim to reinforce and strengthen basic panels. You can see how this looks like in reality. This is upper left figure. Then there is a sketch of a stringer which is laser beam welded to the base metal, and that is shown in the sketch left bottom and on the right. Once we mentioned fatigue, Paris law is next issue to consider. So the famous exponential relation between crack growth rate and stress intensity factor amplitude is also considered here, both experimentally as a part of fatigue testing and then later on numerically. 2 different materials were tested, both aluminum alloys but differently treated. You can see here in red and blue results for 2 of them. You can see that blue one is definitely better in the respect of fatigue crack growth, because both coefficients of Paris law are lower or slightly lower in that case. Anyhow, the focus here was not on material, although it was useful to know which one would be better under amplitude loading, but more on numerical simulation of fatigue testing. So you can see here the base metal and crack, central crack, as simulated by XFEM, Extended Finite Element Method. And you can see some initial results at the bottom to the right, which indicate a rather good agreement between the experimental results, those in red, and blue, XFEM results, those in blue, up to approximately 60 millimeters in more or less linear part of these curves, which represent crack length versus number of cycles. We have almost perfect matching, and then once nonlinearity comes to the life, we can see that crack grows faster in numerical simulation than in experimental research. And that is something that we liked, because although agreement was not perfect, but at least it was a conservative simulation, which enables us to trust our numerical results, at least from point of view of structural integrity. Numerical simulation was also done by Nasgro software to check once again how good is this XFAM simulation, which was made in Abacus by using Orfeo for fatigue crack growth. So here in this diagram we can see the results for stress intensity factor versus crack length, and we can see that XFAM produces slightly higher stress intensity factors, and thus in comparison with Nasgro, once again conservative results. Therefore we finally decided to use XFAM for numerical simulation as defined in Abacus. In this case, of course, there are some other options, but not considered here. Now we can focus on a crack path. This is the most important issue here. You can see one of the meshes, the one with the most refined elements, just 1 millimeter in size. Initial crack length was 14 millimeter. It was central crack as shown previously, and up to 173 steps were simulated. You can see that crack propagated up to 68 steps to reach the finger, both left and right. Some asymmetry has appeared, but almost symmetrical problem, as it should be. After 78 step, stringers are partly cracked. After 130th step, crack is definitely going along the base metal, and then still along the stringers, and finally after 160th step the whole stringer, at least left one, is cracked or broken. So this is quite interesting and not completely in accordance with experimental observations, which are not shown here, which indicate that stringers actually do not break before the whole plate breaks. Two other different meshes were applied, one based on 2 millimeter elements, the other based on 4 millimeter elements, and some characteristic steps are shown in this slide, indicating that at least in one case of mesh with 2 millimeters, actually stringer do not get cracked all the way. So that is probably the best agreement with the experiments. Finally, we have simulated also the most complicated case, and that is with additional 3 clips, which were welded also in an attempt to provide additional number of cycles and to prolong the life. So here we have such a model. Slightly different initial crack length was used, and to be honest, we did not get quite an improvement by adding clips. As you can see, there was a slight increase in number of cycles, 278,000 versus 264,000. So just 5% of improving in fatigue life. Based on the presented results, we can conclude that extended finite element method can play a significant role in estimation of fatigue life of this so-called integral aircraft structure, And especially important is that by this numerical simulation, we can reduce significantly the number of experimental verifications which are very expensive. So the results of numerical simulation are well correlated with experimental results, and conclusion about the behavior of four-stringer plates, also including those with 3 clips, is that XFAM gives good predictions of crack growth rate, but from other practical point of view, let us also note that increase in life was not that much significant, maybe less than expected. Base metal had about 170,000 cycles, plate with 4 stringers about 265,000, and with additional 3 clips 278 cycles. So it seems that stiffness and strength are more important improvements in this case, and also it looks like as that stringers and clips just increased the number of cycles by simply adding those number that were provided by base plate and those number of cycles that was provided by stringers and to some extent by clips. So geometry, which is complex, did not play too much importance. At least this looks like by now we will have to make some additional experiments and then numerical simulation.